Last time in the workshop I was looking at the REVOX C274 reel-to-reel player. It came with blown reefer capacitors, supplied loose in a bag, had no pinch roller tyre and had a broken speed sensor. With all that put right, it ended up even more broken than before. You'll recall that I stopped the job as I was about to move house. So now, some weeks later, I'm in another new workshop, very similar to the last workshop, but with better views. So I now reside in South Wales, in a peaceful location with stunning views across the Tawy Valley. Look at that. There's a variety of stunning spaces here for me to sit and ponder, especially when I run out of ideas during a repair. Unless it's raining. So, where were we? So we turned the power on. And we just get all these lights and no display. And it wasn't do that before I took it apart, so I've got the opinion it's a loose connection. But where? Oh, and now we've got a display. Not the right display, but a display at least. But it's not responding to any buttons. Not at all. Well, the ribbon cables all look seated properly. And that's where I'd expect data to go through. Yeah, definitely, I cannot see that coming loose. Yeah, it's properly clamped down everywhere. So consulting the schematics, we can see that these 7-segment LED displays are driven by these decoder chips here. The inputs to which are on this connector here. That's on connector W1, pins 21, 25, 26 and 23 for the data. And if we look at the layout, we can see W1 is a 26-pin IDC connector, which plugs into the system control board on port number 2. Look, it's got the same pin numbers. That's handy. So I want to scope those serial data lines, so I'm going to need the oscilloscope on. Not forgetting to plug the probe in too. So pin 1 is over here, so pin 26 is here. This is enable low, and it is low, so it is enabled. Pin 25 is the clock. Worryingly, there's no serial clock. And no data. What about this? This is D-Len it's called. I'm not sure what it is, but it's low. All of these signals you can see come from this chip here. That could be a problem. So these are the pins we were probing that should down here. But this 64-pin chip's got quite a lot going on. It does control the whole machine after all. Should at least check pin 33 VCC. This has got 5 volts on it. So here's pin 33. Yep, there's 5 volts. So we should have some data flying about on the address bus and this data bus here. It goes to these 2 ROM chips to start off. Let's check for signs of life. So here's data bit 0. It's just high. And that is stationary. There's nothing going on. Oh, we got data. Oh, what's causing that? And now it's gone. Strange. Now nothing. Nothing again. What's weird? That is strange. Now it's stationary. What did I do? Oh, I've got a feeling I know what's happening. At the heart of any computer chip is a clock pulse driven by a crystal. In this case 4.9152 MHz. And that should be present on pins 2 or 3. Let's check them out. So pin 2, nothing. And pin 3, nothing. We've got no clock. That does explain a complete lack of activity. Let's check it out. So I'm going to take this board out again. Remember not to drop these down the chassis. Now I've got to unplug a load of cables. I forgot about this. I might label them up. I also forgot I did that. This big plug here. It is rather tight again. Doesn't want to come out. It does. Oh yes, and there's the capacitor, the motor, power supply, and the same over here. So here's our unresponsive control chip, and here's a quartz crystal. Oh, did you see that move? Look at that. It's like a wobbly tooth. Well, it doesn't look wobbly from under here, does it? No movement at all. But that's rattling. Well, that needs desoldering. It's typical the pin's bent over. Sort of straighten that. And out it comes. Oh, it's still stuck. Oh, I've unsoldered the wrong part. Now will it come out? Yes. Oh, look at that. Very wobbly. The 4.9152 megahertz is a bit specific. Very specific. I wonder if I've got one. Well, it turns out that 4.9152 megahertz is a sensible and fairly common crystal, as it can be easily divided down to make useful timers, like 10 milliseconds. In fact, on this chip, one of the output pins is actually 80 milliseconds. Using it for something. So let's put it in. Okay, solder both of the parts back in. Plug these cables back in. I'm getting good at this. Let's pop a couple screws in and the board dropping out. So let's give this a whirl. So have we got our clock? Yes. Perfect. Well, if I want to see data properly, I need to ground the probe a bit better. So stick this on the chassis. So clock. Okay. Data. Dealing. Okay. And around the front it looks better as well. Slow speed, fast speed. Excellent. Although these aren't doing a lot. Oh. Well, it thinks it's 1989. Well, it's not. But at least that bit's sort of working. So if I make it think there's a tape there, I can test it out. We'll try play. That looks okay. Oh. It didn't like that. Okay, fast forward. It's going the right way. That's promising. Stopped itself again. Oh, it rewinds. At least the direction's right. But we have got an issue with it stopping on its own. Maybe there's still a problem with the Tacho sensor. So this is J3, so this is the 5 volt rail. That's there, fine. Then over here we've got the output signal. Let's just turn that spindle. We've got nothing. And this is the 0 volts. Yeah. Yeah, I need to take a close look at the sensor board, which means this has got to come off again. Luckily I only put 2 screws in. Better take the socket plate off as well, it's in the way. Well, I better cut this wire off again. There we go. So let's see what's up with this. Put a ground in twice. One for the board, one for the scope. I've got a bit more current than that. 100 milliamps. So just shove the power supply ground in here. So the brown is the plus 5 volts. Ground is yellow. Not exactly conventional, but who am I to judge? Put a bit of insulation over there, look at that. Then we'll finally get our scope probe on the red wire. Okay, let's go in. Tight squeeze again. Okay, power on. 25 milliamps looks alright to me. Well, it looks as good as the day I last repaired it. So, does it work? Yes, it does. That's working fine. There's nothing obviously wrong with this. Must be the way the sensors lined up with these little teeth. Let's stick the vernier in there. Let's measure that gap. What have we got? 8.5 mil. So what's the height of this sensor then? 10 mil. So that means little teeth stick into the sensor by 1.5 mil. Which is that much. Just like that. Well, that looks a bit marginal. I think we've got to lift the sensor up. Maybe make it a bit taller. I mean, there's a few mil of pins sticking out there. Will that be enough? Better turn the 5 volts off before I short it all out. Let's see if I can just push it down with a soldering iron. Just melt these 2 pins while the solder. We'll see if that still works. Change that cable tie, put a new one in like I did before. Let's put the board back on. I'm thinking this might work. Let's put the 5 volts back on. So do we get our signal now? Yes we do. Look at that. Perfect. Well, that was a successful test. Take those off. Can tidy this up as well. Made it a bit curly though. And we'll put the socket plate back on now. And then back in with these plugs. Let's pop another screw up here, hold the board still. It's going to pop a screw in the heatsink, help it draw the heat away. Okay, let's see how we get on now. Just pull these sensors. Will it play? No, still stops on its own. I suspect it's too sophisticated to be fooled by my fingers, so I need to put a tape on this. I can use this empty reel to load the tape onto. It's got this old tape, it's a smaller reel, but it's the right 1/4 inch thing. Don't know how old this is, I suspect it's from the 60s. Although I'll need to take this off, it won't fit on that. Then loop the tapes around all the right places, under the heads, under here, a bit more slack needed please. And up round here, through the hole, and tape it down. See if we can feed the tape on with play. Oh yes, perfect. So that's the start of the tape, so I can reset the counter. I think add the Z location. Now test fast forward. This is perfect. And rewind. I don't take it all the way, it'll rip the tape off the reel. There, if I press Z location, take its way to exactly where we wanted it. Look at that. So finally some success, the mechanism at least is working perfectly well. See if it records. So I'm going to need some input signals. There's one channel. And there's a second. Now I can connect to the outputs. Channel 1 and channel 2. Let's connect these to the oscilloscope. They're balanced outputs, but I'm just using the ground pin to scope ground. It'll be fine. That's a 1 kHz signal. Just zoom in a bit. Okay, we'll set channels 1 and 2 for recording. Press record and play. If we compare that to the input, oh, it's a lot louder. Okay, maybe some adjustments to do. Go back to the Z location. Play that. I mean, it has recorded, it's just not brilliant. Now swap to channels 3 and 4. So I don't want to record on those 2 channels now, just 3 and 4. Ah, it looks like that spiky stuff is noise from the motors. Probably not actually on the tape itself. Interesting. Just going to turn it off before I do any adjustments to this. Just pull the control panel out and latch it in the upper position. That now gives us access to the input board, the 4 record channel boards, the playback amplifiers and the monitor board. I can smell burning. And the smell's coming from down here somewhere. Very strong. I think it's this one. This is Channel 4's record control board. We saw it working, although I don't actually see anything obvious. Given the smell I'm smelling, I'm expecting to see a hole in something. No signs here. Maybe it's not that board. Well, this one's got a whiff about it. God, it is smelly. Can't see anything burnt though. Something's definitely gone on this one though. Can't smell that bad and still be good. I think I better check all of these boards out. They should all be the same. But that one's definitely the smelly one. Channel 3. So I've got the schematic of the record control board. So it's obvious to take the audio input signal, adjust its frequency response, and add the high frequency tape bias signal, and it spits it out on the record head. And of course this board also controls the erase head. After we raise it before it records on it, and it runs from a plus and minus 15 volt supply, which come out on pins 37, 39 and 41. Fortunately, the manual also shows the component placements and the pinouts, and the power supply pins are right at the end of the board. It's got plus 15 volts on pin 37 and minus 15 on pin 41. So I want a dual rail 15 volt supply. So we'll have this set to volts 15. Current will have 0.2 amps each channel. I have to link the positive rail of that side to the negative of this power supply and get it in. So that gives me plus 15 over here, ground, and minus 15 there. So I'll start with the ground pin in the middle, just like that. The pin's quite close together, push the sleeve over it, plus 15 on this pin here, watch it doesn't short across to that, and minus 15 at the top. And power on. At 25 milliamps average, no problems here. Okay, disconnect those, and onto this one. So this is channel 2, minus 15 on there, plus 15 on there, power on. Oh, that's a problem, turn that off quick. We'll put the thermal imaging camera on here, let's turn the power back on, see what's getting warm. Oh, there we go. Yes, this thing here, little MOSFET. So that's over here, Q13, which is one of the pair of MOSFETs used for driving the erase head transformer. And the gates from these go straight across here, straight out of the board. So these gate traces are basically just an antenna. There's nothing holding these off. So it's probably a good idea to connect a resistor on pins 9 and 10 to the minus 15 volt rail. So I'll put another test lead in the minus 15 volts and connect that onto this breadboard, onto the negative power rail, and then put a pair of 100k resistors in. So these should line up with pins 9 and 10. Then just plug these into the pins on the board, just like that. We'll try that now. That's better. 25 milliamps. That board's probably okay. So that's it, channel 2, no problems on there as far as we can tell. And now we're on to channel 3, ground in the middle, plus 15, minus 15. And our little mods pull these clock signals down. And now channel 3. Oh dear, look at that 15 volt rail, that's really shorted. Just scanning around, see something hot, and there we do see something hot. What is that? Well, that's that chip there. Look at that. That's quite a fault there. And that's an LM339. That's a quad comparator, that is. You can see that pin looks a bit hot there. And come to mention it, it does look a bit burnt there, doesn't it? Well, I think we found the problematic one, channel 3. Although what's caused that, we don't yet know. Let's check the resistance across the power supply pins. 2.4 ohms, that's never good. We'll check the outputs on here. That looks okay. Yeah, 10 kilo ohms, looks okay. Skip the power supply. This is an input. That's actually ground. That might be right. This input, 58k, okay. Another input. 4.8 ohms, that's not right. Like this one. 1 meg. Interesting. Inputs on here. 5.7 ohms, that doesn't measure good. 5 ohms again. 4.8. Yeah, 4 ohms there. And finally we've got the output pins here. 2.5k. 16k. Looks like this chip's got damaged inputs. So that chip is IC8. So IC8, as I mentioned, is a quad-con parity, so the 4 elements of it are here. The input on pin 4 is actually ground, so that's alright. But these inputs here, yeah, these aren't connected to ground. Wherever there's a resistor, it's 47k to ground. This resistor is 22k. Yeah, there's no 4 and 5 ohms here. There is a 22 volt supply here feeding through this relay coil, and it could make its way through these 2 diodes if they'd shorted, that is. Let's check these out. So we've got D7 and D8. No problems there. I suspect this might be an isolated failure. Not sure anything caused it to fail. But I've got to replace it anyway. Now hopefully that'll come out. Oh, it's a little bit hot still. There we are. Oh, you can see where the magic smoke came out there. All little splits in the bottom of it. Yeah, that's definitely cooked. Fortunately, the LM339 is a very common chip. Not hard to find. Now just solder it back in. Only 14 pins on these. Just connect the power supply pins again, 15 volts on there, ground in the middle, and minus 15 volts on the end. And our clock signal tie down resistors. Let's see how much current it draws. Perfect. Same as the other 2. Oh, very strange. Random failure. Hazard of working on vintage stuff, that is. And finally channel 4. Not expecting trouble with this one. And the pull down resistors. Let's see how much current channel 4 draws. Same as the others. Perfect. But at least there's no shorts on the board. Well, that's good news. Can take that apart now. Power supply off. So I can put these boards back in. Give it another try. You have to give these boards a little bit of a wiggle. They don't line up that nicely. As long as the pins are straight, it should go in. Okay, power on. Current looks nice and healthy. No drama from here. So I want to record this signal. Actually, I'm going to record all 4 channels. Check that actually do something. In fact, so I can differentiate these, I'm going to change the frequency to 2 kHz. Just to make sure it's actually a new signal. Because I've already put 1 kHz on this tape. I'll put it on reproduce. record and play. While they're worrying, we've got nothing on channel 3. We'll just fix that board. It's not recording. Oh, it's just come back. No, it's not coming back. Look, it's 1 kHz, it's not 2 kHz. Okay, and pull channel 3 board out and channel 4 and swap them over. See if the fault moves with the board. Power back on. Before I do that again, I'm going to go onto the input. I'm going to crank these up so the signal's much larger so we can tell them apart. So what we're looking for is to see channel 3, is it recording or not. We should be looking at a large 2 kHz amplitude. I forgot to put it on reproduction. You can hear it now. Ah, we don't have it. Channel 3 is still not working. There's a little bit of noise there, but once we get to about 30 seconds, we'll see where the old recording changes over. Yeah, it's not erasing either. Neither recording nor erasing. So channel 3 is neither erasing or recording, and it's not the record control board. We swapped them over. What could it be? To give us some clues into what's happening, it'll help to understand how tapes actually work. A blank tape's a piece of plastic with some iron oxide on it, or various other magnetic elements. The magnetic particles are magnetised in a random fashion on a blank tape. It's just random. You might get a bit of hiss, but nothing really. One of the problems with magnetic tape is it's actually quite hard to magnetise, well, magnetise permanently. So you have to apply quite a strong magnetic field to orientate these in the right way. So if we had our audio, the signal's going to be quite small, insignificant for the magnetising of the tape. It won't actually record anything. So we have to apply something that is strong enough to magnetise the tape, and we call this the bias, which is generally a high frequency sine wave, typically around 100 kHz or so. So you'll never hear it. The trick is to actually mix these together to create an amplitude modulated signal, very much like AM radio. And because the amplitude of this is so much higher, that is enough to magnetise the tape. And when it's played back, much like with an AM radio, you just filter this high frequency out and you're just left with the audio signal. And in fact, when you want to erase a tape, you just apply the bias signal with no audio. That will erase it. That's how it's done. So I suspect we got a problem with the bias. So that's our schematic. We can see the audio input signal comes in the circuit here, EQ circuits, blah blah blah, and it gets mixed over here. This is where the bias is applied. And we see the same thing for the erase head. Very similar circuit. The bias is applied here through this transformer. No audio is added at all. But I do notice these two transistors, these are familiar, these were stuck high, weren't they? They were on. And these are clocked externally. These signals here, Q and Q bar, 156 kHz. In fact, the same two signals are used to drive the recording bias. So the pins of interest, pin 30 is the audio source. We'll check something's there. And pins 19 for the 153 kHz bias clock. So I'm going to need another scope probe. Glad I got enough channels. So I need to activate that channel. Channel 3. We'll stick that sort of in the middle. So here's the back plane, and record channels are here. Channel 1, 2, 3 and 4. We've only got input signals going on channels 3 and 4. Pin 30. So that's this one here, the third one down. There's our audio signal. Is it on channel 3? Yes, it is. So let's look at the bias clock, pins 9 and 10. Well, there's something there, look. Let's sort the scope out. We can attenuate the signal if I switch this into times 10 mode. First thing to do is change the triggering. You want it to trigger on channel 3. You want to wind the horizontal in, expand it. There we go. There's our clock signal. So here's channel 4 again. Q is there. Q bar. Just the same. Perfect. Channel 3. Oh, nothing. Look at that. There's our problem. Q bar. Nothing there either. To prove the point, channel 2. Yes, we've got Q. Q bar, yes. And then channel 1. Yes, we've got it. Q bar. Yes. So we've identified the fault with channel 3. The bias signals are missing, but where do they come from? Why have they gone? In fact, we can quite easily see that the bottom 2 pins here on every trace, they all sort of go to this chip here. What's this? I can just make out HC175E. Let's check out the drawings. So there's channel 1, there's channel 2. There it is. IC1. And sure enough, it does drive the Q and Q bar signals to all 4 channels. So it's a 74HC175. That is a quad D-type flip-flop. So it takes a single clock signal in and essentially divides the frequency by 2, spitting the same thing out on all 4 channels. I've done about 300 kilohertz, and that's a bit of an approximation, but yeah, that signal comes on the system control board. Ultimately that will be derived from the 4.9152 megahertz crystal. And if you're wondering if the 2 problems are linked to the faulty chip, I don't think they are. I don't see how they can be. The Q and the Q bar signals only go to the gates of these MOSFETs. And these 2 over here, they're extremely high impedance inputs. They're not going to put any load onto that flip-flop chip. I just pulled out the magic chip drawer, see what we've got. We start off with the low part number, 7404 and that, and we work our way up. On the top of this list, where does it get to? 74LS164, neat, page 2. And there we go, 74LS175. Interesting, these are LS, this is low power Schottky versions, not the HC versions. The HC variant, or the high speed CMOS, will actually work on a slightly wider supply range, up to 6 volts. The LS, on the other hand, can only do about 5¼ volts. It's a bit twitchy. So check what the voltage actually is across here. 5.3 volts. That's a little bit over what the LS version can handle. This chip's not actually connected to ground, it's actually connected to the -15 volt rail. The positive supply comes through ground via a resistor and a 5.1 volt Zener diode. So it's supposed to have 5.1 volts across there, but it's a little bit high, it's drifted a bit. I could see changing this diode, see if I've got one that's closer tolerance, gets it under the 5.25 volt threshold. Or I could just wait for the HC version of the chips to arrive. They're still readily available. So on reflection, I've decided I'm going to wait for the right part to come up. I'd rather have a bit more headroom with the voltage and some marginal bodge, which could go again. So, with that in mind, stick around for part 3. Catch you next time. I think we got our shot then.